All right, in this video we're going to talk about a fundamental law called Gauss's law. In words, Gauss's law can be written like this. The net electric flux through a closed surface is equal to the charge enclosed by the surface divided by epsilon naught. In symbols, it might look something like this. So here's our electric flux. We're thinking about it, the net electric flux through a closed surface is equal to Q enclosed divided by epsilon naught. Now, how do I actually determine Q enclosed? Sometimes it's relatively easy when you have maybe a collection of positive, negative, positive, positive, negative. Maybe you have a collection of point charges that look something like this. And all you have to do is you choose a surface and you count up how many charges you have enclosed. So maybe I choose a surface that looks something like this, and I might add up that I've got 2 positive charges and 1 negative charge. I could add them all up to get my Q enclosed. So many times when we're using Gauss's law, we're going to do something like this to help us understand how much charge is enclosed by a particular surface. I might call a surface like this a Gaussian surface whenever we're using Gauss's law and we're thinking about this closed surface. I'm thinking about what I'm going to call a Gaussian surface. And usually you have control over the type of surface that you choose to use. So in further integral form, writing the definition of the electric flux in, your electric flux is your integral over your closed surface, right? That's what this double integral with a circle means. It means your integral over your closed surface of E dotted with the area element around that surface, and that's equal to Q enclosed over epsilon naught. So why might we actually use Gauss's law? We've been thinking about how you can calculate the electric field from some charge distribution. But Gauss's law is extremely useful when your charge distribution has just the right symmetry and when you can choose a Gaussian surface to fit that symmetry. The two conditions that are important to consider when you're choosing a surface for your charge distribution is you want E and dA to be parallel, right? That will give you the cosine of that 0 is 1. That'll give you your maximum possible flux through that little area element. And you want your electric field to be uniform along the surface. So as you move along your area, your electric field should stay the same magnitude over that area. Let's see how we can apply this to a point charge. We know the answer to this already. If I want to determine the electric field of a point charge, we know that it is kq over r squared. So what we're going to try to do here is recover that answer using Gauss's law. First, we're going to talk a little bit about Gaussian surfaces. So what I'm going to do is I'm going to draw 3 different point charges. Here's my plus q, here's another plus q, and we'll do one more plus q down there. We're going to think about 3 different Gaussian surfaces and how we can apply these two rules there to choose a Gaussian surface. So a surface that I might choose is I could choose a cube, right? Imagine I take my charge and I place it inside a little cube there. And now I need to see if those rules are satisfied. I could draw my electric field of my point charge. I know that positive point charges have a radial electric field pointing outwards. But I can start to see that when I draw more electric field lines, even though there are some locations where the electric field is perpendicular to the area, not all locations are perpendicular to the area, right? So here's a good example. The little local area element is right there, and that's not parallel to this area vector, to this electric field vector here, right? So my E and my A are parallel here, but they're not over here. So this would not be a good choice also because my electric field at these different points around my cube here are farther away or closer to the point charge in the middle. So my electric field is going to vary as I move around that cube. So this isn't a very good choice. I'm not going to choose a cube for my Gaussian surface for a point charge. I could choose another surface, which you'll see often when we talk about Gauss's law, and that might be a cylinder. And again, you have the same sort of problem. My electric field is parallel to my area vectors at these locations, but when I start drawing more electric fields, I start to quickly see that my electric field and my area vectors don't nicely align. And similarly, my electric field is changing in magnitude as I move around that surface, so this would also be a bad choice. The last surface that I'm going to draw, or you could choose many different surfaces, but the one that we're going to use to help us find the electric field of a point charge, and what you may have already thought about, is a sphere. So let's imagine that I am putting that charge perfectly in the center of a sphere there. And this is going to be my Gaussian surface. And now I can see when I start drawing multiple electric field lines that my electric field and my area element around this surface are parallel to each other at all locations. And assuming that the point charge is in the dead center of this Gaussian surface, the distance from the point charge to the surface will be the same all the way around the sphere. So my electric field will be uniform in magnitude all around the surface of that sphere. So this is a good choice for this charge distribution, right? This is the kind of game you have to play when you're trying to choose a Gaussian surface. All right, so we've chosen our Gaussian surface. Now let's see how we can use Gauss's law to help us find the magnitude of the electric field. I'm going to rewrite Gauss's law here for us. So this is our integral over a closed surface of E dotted with dA is equal to Q enclosed divided by epsilon naught. In this case, my Q enclosed, I'm just adding up the charges inside that sphere, just plus Q. So I'm going to write plus Q over epsilon naught. Now what I want to do is I want to find the magnitude of my electric field. So I'm going to quickly first identify the parts of my integral before I start to integrate. So what I'm going to do here is I'm going to write that my electric field is equal to some magnitude E times r hat. So what I'm doing here is I'm saying I don't know what my magnitude of my electric field is. I'm just going to call it something E, and that's the thing I'm going to solve for. I'm going to define my dA in a similar way where I will write dA r hat, right? I'm just defining and making it clear the directions of these vectors. This is my area element along each of these pieces. Here's a little area element coming off of that Gaussian sphere. It's a little hard to see. You have a little area element all along your sphere there. So now what I'm going to do is I'm going to take those and plug them right into my into Gauss's law here, and I will write down my integral over my closed surface of E r hat dotted with dA r hat. So I'm going to simplify this a little bit now. I've got r hat dotted with r hat. That gives us 1. This ends up being, I'm going to put an equal sign right here. Surface like this, so integral over a closed surface is E times dA. And now another thing that we identified was that my electric field does not change over that area. That lets me pull the electric field, this magnitude here, right out of the integral. So this ends up being my integral of E on the outside, integral over dA. So I pulled E out of my integral because it's not changing over my surface, EDA, and now I'm integrating over the surface of this sphere. This will just give me the total area of the sphere. So if I am some distance r, my Gaussian surface has a radius of r, then I can start to write that my electric flux now is E times 4 pi r squared. So now I've found my electric flux that is going through my Gaussian surface. And so I'm going to take this and plug it back up here, and I'm going to rearrange and solve for E. So let me just replace this really quick. So I've got E times 4 pi r squared is equal to plus Q divided by epsilon naught. I'm going to take this and divide it over. So this gives me that E is equal to 1 over 4 pi epsilon naught times Q over r squared. And remember that we can replace that 1 over 4 pi epsilon naught with the electric constant K, Q over r squared. And that's exactly what we were expecting, right? We were expecting to get that our electric field magnitude of a point charge is kq over r squared. Now remember, this is just my magnitude of the electric field. If I want the total electric field, I need to make sure that I include over r squared the r hat direction. So this is an example, a relatively straightforward example of how to use Gauss's law, which we will start to explore more with different geometries and different charge distributions coming up.